My name is Steve Boggs. I'm the chair of the physics department here at Berkeley. And on behalf of the department, I want to welcome everybody to the 2014 Emilio Segre lecture. So this is an annual event in the department. And we're really fortunate this year that our presenter is our former chancellor, Emeritus Chancellor, Robert Birgeneau. And without further ado, I am going to step aside and give the stage to our current Chancellor, Nicholas Dirks, who's going to introduce the speaker. So, Chancellor Dirks.
Thank you, Steve, and it's my great pleasure indeed to officially welcome you to the annual Emilio Segre Lecture. This event, which has been generously underwritten by Raymond and Beverly Sackler, is brought to you each year by the physics department. I will try. I will try. It honors one of our great experimentalists, Emilio Segre, who together with Owen Chamberlain won the Nobel Prize in 1959 for their discovery of the antiproton. Now today is particularly special, I think, for all of us, because my favorite Berkeley physicist is delivering it. Now, I'm sure you know, and I certainly know because I've read almost all of them, Professor Birgeneau has given quite a few speeches over the past decade here on campus. But what I have discovered is that having read through each one of these speeches very carefully, and I will tell you, Bob, I have on occasion cribbed. That's what we do sometimes, but not tonight, not this afternoon. They have been devoid of any serious reference to superconductors. So we organize this as a special opportunity to redress that balance, but indeed at the same time to welcome Bob Birgeneau back to the faculty in physics, which of course he never left all the time that he was in California Hall, but which now California Hall has released him to engage full-time as opposed to just between midnight and 6 in the morning. Now, Bob doesn't need any real introduction here, indeed anywhere across campus, but I would like to just briefly review some of his daunting accomplishments, academic and administrative, in order to introduce him this evening. He was chancellor of this great university from 2004 until 2013, and I have to say that he did such a spectacular job that he managed to see us through some of the most difficult years in the history of the university with a record not just of continued accomplishment, but a bequest to me, which is that the University of California at Berkeley is in better shape than ever before. I, therefore, will take advantage of this opportunity to thank Bob again for all that he did to persevere in the most difficult of times and circumstances, to relentlessly advocate for the university and find ways to adjust many of the models that have traditionally underwritten support for the university and made it come out not only doing well, not only surviving, but indeed thriving so well. And in addition to that, he's been a great mentor for me. So I have to say thank you, Bob. Now, when he's not working to save public higher education these days, and I'll say more about that in a second, Bob, of course, is a condensed matter physicist. His research is primarily concerned with the phases and phase transition behavior of novel states of matter. While we are all familiar with changes of phases in our daily lives, my scriptwriter wrote something about water being transformed to ice, but actually my mind thinks about the phases that I don't really get to enjoy very much between one meeting about budget and another meeting about protest and another meeting about, so I'll use that as my example of phases in daily life. What Bob does is to explore these properties in more exotic systems, allowing him to study superconductivity as well as magnetism in multiple dimensions. And Bob received his PhD in physics from Yale in 1966, with Professor Werner Wolf. He was on the faculty of Yale for 1 year and then spent a year at Oxford University. From there, he went to Bell Labs from 1968 to 1975 before moving to MIT, where he was, of course, not just a professor, but also the Dean of Science. He became, in the year 2000, the president of the University of Toronto, and of course, in 2004, decided to come to the finest university in North America, our very own, where he not only became the 9th Chancellor, but also the Arnold and Barbara Silverman Distinguished Professor of Physics, Materials Science and Engineering, and of late, Public Policy as well. Bob is a fellow of the US National Academy of Sciences, the Royal Society of London, the American Philosophical Society, the American Academy of Arts and Sciences, and other scholarly societies. He's the winner of the Carl Taylor Compton Medal for Leadership in Physics, the 2008 Academic Leadership Award from the Carnegie Foundation, the Oliver E. Buckley Prize in Condensed Matter Physics, and that is just a small sampling. Now, as I alluded to before, Bob's commitment to public higher education, as well as, of course, to the University of California at Berkeley, did not end when he handed over the keys to me. He is currently serving as the chair of the Lincoln Project of the American Academy of Arts and Sciences, an endeavor that is working to assess threats to public higher education, developing recommendations to preserve the strength and diversity of our country's colleges and universities. And he gave a presentation to all the new inductees of the American Academy of Arts and Sciences last Saturday in Cambridge, Massachusetts. And I heard throughout the room the sense of appreciation and indeed admiration for the work that you're doing, Bob. So it is a great pleasure indeed to introduce you tonight to speak on superconductors, old and new. Please join me in welcoming Professor Robert Birgeneau.
Thank you so much, Nick. Although those kind of introductions are always a little bit scary because they make expectations so high. But I'm pretty confident that this crowd is going to be a little friendlier than literally the last time I talked in this room when I literally needed a police escort to get out. That's actually true. It was, anyway, it was interesting times the last 4 or 5 years. Anyway, it's just such a pleasure, and it's great to see so many friends and colleagues here and so many students at this talk. And as I said to a number of people, as soon as I get to the point where I'm making a complete mess of it and nothing seems to make sense, please interrupt me, and I'll try and go back and do a better job of it. I want to actually, first of all, I want to thank all of my former students and graduate students and friends and colleagues who have come from afar for this, but most especially for the symposium tomorrow. People who, sort of third parties who looked at the lecturers in the symposium said, hey, wait a second, this is a who's who of modern condensed matter physics all coming to talk tomorrow. So it will be really exciting, and I'm sure that I will learn a lot. I obviously also want to thank Marvin Cohen, who actually, it was first his idea. Marvin, where are you? Yeah, there's Marvin over there. When I haven't been a big believer in like having 50th birthday parties or 60th or 70th or 80th or, God forbid, 90th birthday parties, and had said that I really wasn't interested in that kind of celebration. But I happened to mention in a conversation with Marvin that this week actually turns out to be the 50th anniversary of my first publication in Physical Review. And Marvin thought, now that's worth celebrating. So I thought, okay. And I need to explain to everyone here, I was 21 years old when I did that research. And embarrassingly, for 2 decades, it was my most cited paper. So I sort of hit my peak at 21, but thanks to a few of the people in this audience, actually, I managed to come back to do something a little better than when I was 21 years old, 2 decades later, I guess, 2.5 decades later. So the other thing is I want to thank the Sacklers. This is actually my second time as a Segre lecturer, which might surprise Steve. But in fact, my first time was as the same thing, Emilio Segre lecturer, but at Tel Aviv University. and also funded by the Sacklers, and Amnon Aharoni and Ora Anton Ullman, where are you? So they were my hosts in Tel Aviv at that time, and it was just really wonderful. And as a result of that, I got to meet the Sacklers, who are wonderful people and who have subsequently been very generous to Berkeley. And they obviously were great admirers of Emilio Segre. So thank you also to them. So what I want to do is today is just to do a little bit of history of the field of superconductivity, a field in which I'm sort of relatively new working in, actually. So I didn't really start working in superconductivity until what will be halfway through this lecture. But I went back to sort of try and understand the roots of the field, and as you'll see, they're quite interesting. And one of my themes is going to be that even when you think a field has come to maturity, which I certainly did for superconductivity in the 80s, serendipitous discoveries, usually made by material scientists, not physicists actually, although in this case it was physicists who did it, or a partnership between a physicist and a material scientist. People could suddenly discover new phenomena that completely contradict what we academics are teaching in our undergraduate and graduate courses, and which are major surprises, and show how shallow our understanding actually was at a particular stage. And in the field of superconductivity, this has now happened twice in my career, very surprisingly, actually. And so I'll tell you about those surprises, or at least why, maybe if you're smart enough, they're not a surprise, but at least to people like me, they are a major surprise. So I'll tell you a little bit about those. So this is about basic research. And with Jim Simon sitting here, Jim and I are working together. We mentioned the Lincoln Project, but another project we're working on is to try to enhance support for an understanding of purely discovery-driven basic research. I mean, we of course all care about research which has an impact on society, but there's an important role to play for research which is entirely driven by our desire to make new discoveries and to understand nature at a level that's deeper. So I was looking for sort of quotes to sort of, to set the theme of this talk. And there's a lot of people here who spent some part of their life at MIT, and so they will remember Vicky Weisskopf, and even if you didn't ever meet Vicky Weisskopf, you know him as a great person. So there's several quotes which we came up from Vicky. So first one is, we need basic science not only for the solution of practical problems, but also to keep alive the spirit of this great human endeavor, right? And maybe we can even forget the first. Second, which is relevant to two talks you're going to hear tomorrow afternoon from Bob Haas and Evelyn Hammonds from Harvard, human existence is based on two pillars, compassion and knowledge. Compassion without knowledge is ineffective. I think that's really important. But of course, also knowledge without compassion is inhuman. And finally, for those who know Vicky, this is a pure Vicky Weisskopf quote, but I quite like it. When life is hard, which it is often for many of us, there are two things that make it worth living, for a physicist at least: Mozart and quantum mechanics. I should have also mentioned three, my wife, because she's sitting here. And with Bob Haas here, I won't speak for Bob sitting in the front row. Bob, maybe for us it's the Cal Bears and quantum mechanics, but anyway, okay. Not these past 2 years, but that's a separate story. Okay. So I want to acknowledge the newer members of my research group here at Berkeley. So these are almost entirely people that have been working with me here at Berkeley from the beginning of my time as Chancellor, when I had a certain level of research, and which is now, I'm pleased to say, as of September 1, my sort of group is back to where it was in equilibrium many decades ago when I was a regular professor at MIT, so I'm very excited about that. And I've really been very fortunate throughout my entire career to have outstanding students and postdocs, many of whom are here going back many decades, and recently here at Berkeley, and I won't read their names, and then a number of collaborators, including Edith Bouret, who's here. Edith, where are you? Who's been critical in our crystal growth effort. And Donghai Lee, Donghai, just saw you right. And Alessandra, I don't know if you made it. And then John Tranquata, and then Stephen Wilson, who just moved to Santa Barbara. Stephen, where are you? Great, so Stephen's way back there. Okay, good. So in this talk, there's going to be 4 sections, although it's already 25 after 5. So we'll see how many of the sections that I get to. First, I'm going to give you a little bit about the history of the field of superconductivity, which is quite interesting. Secondly, I'll tell you about traditional superconductors. Then I'm going to tell you about the first sort of major shock that happened in this field. And I knew the people who made the discovery well personally and interacted with them during the time period that they made the discovery, so I'll give you some inside dope that's not written down anywhere, so we can share the gossip. Then I'll tell you about the iron Pnictides, and by then I'll probably have run out of time. So, but I'll then jump to the lessons in the end. So let's start with the history. So, of course, the great person in this field who began it is a Dutch physicist by the name of Kamerlingh Onnes. And Kamerlingh Onnes's achievement, actually, the signature achievement, was through the person on the left and several people like him figuring out how to liquefy helium so that you could reach temperatures as low as 4.2 Kelvin. And in fact, if you pump on it, you can get all the way down to nearly 1 degree. And so in Kamerlingh Onnes's lab, for the first time in history, people could get down to extraordinarily low temperatures. And one of the reasons, and I think it's a lesson to us all even today, is that Kamerlingh Onnes really appreciated the importance in experimental physics of really good technical people. So they had a school that trained these gentlemen who wore blue jackets, and they were called blue boys, which is perhaps a little condescending, but it was Dutch society at that time. So they made this incredible apparatus that could liquefy helium. And it's a complete aside, by the way, but it turns out if you read the logbook, I got up on the history of this, they also, Kamerlingh Onnes, besides discovering superconductivity, also actually discovered superfluidity in helium. But superconductivity he recognized, superfluidity he didn't. So someone else got the Nobel Prize for that. But he actually produced the first superfluid, okay, in the lab. Pretty astounding. So this is the famous resistance plot by Kamerlingh Onnes. Now, of course, they had this dewar, which would get down to liquid helium temperatures, 4.2 degrees Kelvin. And the history around the actual discovery is murky. And it depends how friendly the writer is to Kamerlingh Onnes, which version. The version that I trust the most, because it's from the most people I think were most objective, and I just reread a couple of days ago back in the history books, one of these accounts. Tells the story about Kamerlingh Onnes's graduate student, whose name was Gilles Holst. In fact, I know that name because I gave part of this talk a few weeks ago at the University of Colorado, and someone asked me what was the name of the graduate student, and I couldn't remember it. So in between, I did research. So the graduate student's name was Gilles Holst. So he had this apparatus. And so Kamerlingh Onnes had the idea that remember, there was no quantum mechanics then, right? Because it's 1908. So he had the idea that the resistance in a metal would change dramatically between the liquid state and the solid state. And that is between a liquid and a crystal. And so a way of measuring that was to take liquid mercury and to cool it down, and to measure the resistance of liquid mercury, go through the liquid-solid transition and see what happened, right? And to see what periodicity would do to resistance. So he then charged Holst to make an apparatus, which actually had 3 in series samples of liquid mercury with actually mercury leads into it to measure resistance. So Holst does this, and he's doing it on his own, and he did. And then he discovered that the resistance at some very low temperature, 4.2 degrees, went to zero. There was no resistance. So he was, of course, convinced that he'd made a mistake. In fact, the theory at that time said that the resistance should go to infinity. So theory predicted the exact opposite. Remember, there was no quantum mechanics, right? So in a non-quantum mechanical world, the electrons were going to stop moving at low temperatures, and therefore resistance would be infinite. Instead, it goes to 0. So then Holst repeats the measurement and gets 0 again. Then he takes it to Kamerlingh Onnes, who decides that this graduate student is obviously incompetent, and he literally threw the apparatus away. So then he redesigned it, having 7 resistors in series, 7 pools of mercury instead of 3, and redid the measurement, not allowing the graduate student in the lab. And then he reproduced the graduate student's result. And for this, Kamerlingh Onnes got the Nobel Prize. Now, when I was the age of most of the people in the top half of the room, and I knew this story, I thought this was the worst thing I'd ever heard in my life. But somehow or other, when you're celebrating your 50th anniversary, it doesn't seem as awful as it did 2 years ago. So Kamerlingh Onnes, therefore, made this extraordinary discovery, and he published the paper on his own, single author, just Kamerlingh Onnes, okay, right? Holtz then helped the experiments get better by helping Onnes to do chemical analysis and to clean up the mercury, et cetera, right? But if you read a Dutch version of this, which I did also in a Dutch magazine, then the story comes out very differently, and the student's infinitely grateful to Kamerlingh Onnes for the privilege of being around him. It didn't end that badly, because it turned out that the student got his PhD, not in superconductivity at all, but doing other kinds of measurements. He was the first person hired by Philips to set up a research lab. He became the head of Philips Research Lab. And some of you in this room will know Cherry Murray, the Dean of Engineering at Harvard, a great scientist, right? And she just gave the Gilles Holtz lecture at Eindhoven. So Gilles Holtz became very famous, and famous people like Cherry Murray give a lecture in his name, so okay. Personally, I'd rather have the Nobel Prize. Okay. The next discovery, and this will already, if we tried to explain it, become too technical, but is really important, is for superconductivity, it's not enough that it's a perfect conductor. In fact, we now have other examples in nature of a perfect conductor. There's a second effect, which was not discovered until 1933, much later, which is that a material which becomes a superconductor not only conducts electricity perfectly, but it also is a perfect diamagnet, which means it excludes magnetic fields. A perfect conductor that's not a superconductor will not exclude magnetic fields. So there's an essential difference between something that's just a perfect conductor and something that condenses into the superconducting state and has what in our modern language is the relevant broken symmetry. Okay. That then leads to all kinds of fun things that you can do, like levitating magnets. Didn't I once see a picture of you being levitated standing on a magnet? You can levitate Marvin Cohen. I mean, this is like a miracle. Okay. So this is the second thing. I have to say as an aside, I don't know, how many here have ever played the game Trivial Pursuit? If it was in Canada, everyone would have their hands up. So that's Mary Catherine's brother's game. So we were on vacation when high temperature superconductivity got discovered, and I was explaining to him what it meant. And he's sufficiently savvy, his very first question was, yes, but does it work at room temperature? Because he could think of the number of games that you could make with levitated magnets that would far outstrip Trivial Pursuit in its success. Okay, so when you discover a high temperature superconductor, patent it and then go to Mattel immediately, because that's where the big money will be. Anyway, so many of the very best minds, people like Landau, the London brothers, worked on the theory of superconductivity. And it represented an extraordinary theoretical challenge for 5 decades, right? And its ultimate solution is one of the great triumphs of theoretical physics, of modern quantum theoretical physics. Really magnificent. And that's by these 3 gentlemen. John Bardeen, who's in the middle, Bob Schrieffer on the left, and Leon Cooper on the right. And Leon Cooper was a postdoc at University of Illinois at that time. And without going through the details, although I'll show you a schematic picture, had this idea that if you had an attractive interaction between electrons, they might pair and break off from the Fermi sea, but for a single pair. And Bob Schrieffer was an undergraduate at MIT, and he knew about superconductivity. And Doug, I heard this from Bob, I think it's a true story, that he decided that for his PhD, he wanted to take a crack at solving the problem of a theory for superconductivity. and deliberately went to the University of Illinois at Urbana-Champaign to work with John Bardeen because John Bardeen was the smartest person he had ever met. And so John Bardeen had already discovered the transistor, non-trivial contribution, and got the Nobel Prize along with Shockley and Bratton, right, for discovering the transistor. I once visited Bardeen in his office, and he was like in the basement building with old steel case furniture. I mean, he was the ultimate physicist, a wonderful, wonderful man. So Schrieffer goes to Illinois and starts working on theory for this. And Cooper was at Illinois, had this idea of what are called Cooper pairs. And the challenge was to generalize it from 2 electrons to 10 to the 23rd electrons with quantum many-body theory. And Schrieffer basically did that successfully with a great triumph. It's interesting that all the great Russian theorists who were working on it at that time said that if they had read Cooper's paper, they would have solved the problem first. Right? Doug, do you think they would have? Doug's too nice a guy to be, okay. And the sort of basic idea, but this can only be schematic, is that you would think electrons would always repel each other. But in fact, when you look at the interaction of the electron with the lattice as it's going along, the lattice responds. And so you can think heuristically that one electron goes through, and that makes it easier for the second electron to go through. And so that ends up leading to a net attractive interaction between the electrons, so they want to bind together. But because of statistics, they can only bind together. Let's see if this works. Yeah, they can only bind together, and this turns out to be really important for what's about to come. If you have 2 electrons, they have to have opposite momentum. But more importantly, each electron has a spin, of course, right? It's like a little magnet. The spins must point in the opposite direction. So that's critical. And so in order for the electrons to bind and to have a superfluid, the electron pairs must have their spins antiparallel. That's at least in all superconductors we know. Okay? And so what would happen if I have this pair of electrons going along, forming a Cooper pair, and something caused one of the spins to flip? If that happens, then the theory tells you that the pair will break up and you'll lose the superconductivity. So that was one of the early predictions of their theory. So some decade later, a young experimentalist by the name of Brian Maple, who's at San Diego, did this really magnificent experiment, which I really love, in which he decided to take a superconductor, that's lanthanum aluminum 2, and to put in a very small amount of gadolinium. Now, why would you do that? You do that because gadolinium turns out to have a very large spin. It's a very strong magnetic atom. And so the idea was that if this theory is correct, that the Cooper pairs must have their spins antiparallel, and you've got some little magnetic dipole sitting there, this pair will come along, it will see the gadolinium spin just sitting there, they'll couple, and it'll flip it. It flips it, and then they repel each other, then there goes the superconductivity. And so in this experiment, if you look at the origin, you notice at the horizontal, you notice it's n over n critical. But n critical is about 0.5%. So this tells you that 0.5% of a magnetic impurity is enough to completely destroy the coherence of the Cooper pairs and therefore destroy the superconductivity. So this is a very famous result. It's such an elegant experiment. There's even a theory for it called Abrikosov-Gorkov theory. The Russians recovered. They didn't know about, once they knew about Cooper pairs. And Abrikosov and Gorkov did this very, very beautiful theory, which quantitatively predicts the effect of magnetic impurities on the superconductivity and the fact that it will vanish at well, I presume they adjusted n critical, but that it vanishes very small. So this is important because it meant that all of us who thought about superconductivity thought magnetism, spins, and superconductors are anathema. You can have one and not the other, and that is it. Okay. Then this extraordinary thing happened. And so in 1986, and with all my apologies to John Clark and a couple of others, I remember that semester well, because I was teaching the undergraduate solid-state physics course, a course that bridged between undergraduate and graduate school. So that some graduate students took it, some undergraduates took it. And all the students in the class were anxious, especially at a place like MIT where everyone's anxious anyway, but that's a separate story. but they were more anxious than people usually are at MIT, and trying to figure out what field they should go into in their graduate work. And I remember explicitly, and I feel bad, John, saying to the students, you know, they're really down into the fine details of superconductivity, so that's a field you probably shouldn't go into, right? I apologize. I was wrong. Okay. And then in the middle of the semester, I'm reading a paper, and there was this announcement that this extraordinary thing had happened, where a new family of superconductors had been discovered, and with rocketing up high in temperature, the community responded that this was a miracle that you had such high temperatures. Actually, as I hope I'll explain successfully, if the temperature didn't go up at all, it's still an extraordinary discovery. And I'll try and make that clear, okay? So all the attention is on that explosion in the temperature, but that's not what's so remarkable, at least from my point of view. Now, this also has some personal history, which I want to tell you about. So the two people who made this discovery are Alex Mueller and George Benedek. George Benedek, I mean, a lot of people here know George Benedek, George Bednarz. George Benedek was a colleague at MIT, sorry, George Bednarz. So let me give you the background to this, and this is what I'm about to say is absolutely true, and it's not in any of the history books yet. So 2 years, so this is 1986, they did the work, discovered this new family of high-temperature superconductors, and they got the Nobel Prize 1 year later, which is extraordinary. That almost never happens within 1 year. So it's 1984. I was working with a fellow by the name of Paul Horn at IBM Research Labs in Yorktown Heights. And we were collaborating on, we were at that time doing some of the early experiments using synchrotron radiation to study phase transitions in 2 dimensions. And some of the people involved in those experiments are sitting here, like Pete Stevens. And so I was down at IBM, walking down the hallway, and there's Alex Mueller. So remember, this is 1984. So Alex had been head of IBM's research lab. And he had just basically been, I don't want to quite say turned out, but he would rotated back down to the bottom. And he was a little bit bitter about it, actually. He had done a good job running the lab, and he was not a happy man. Now, fortunately for him, they made him an IBM fellow, which at that time may have been the best job there was in science, because you got to do whatever you wanted, you were well funded, and you reported to the president of IBM. Now, the president of IBM has less than 1 microsecond a year to talk to you. So it meant you can do whatever you want and you have no supervision. I mean, this is and you're well funded. I mean, is there ever a better job for a physicist? So Alex was really grateful. He actually thought I had had something to do with, personally, with him getting that position. And I took credit for it, but actually I had nothing to do with it. But so I'm talking to Alex, and I said, you know, so he went through this thing of, you know, his career. He had done a magnificent job on doing very beautiful, elegant experiments on phase transitions in oxides like strontium titanate, and stimulated by Marvin Cohen, actually, and the theory that Marvin had done at that time on superconductivity. And so Marvin's papers on superconductivity and strontium titanate got him thinking about superconductivity in oxides. So, and there was a theoretical paper which came out at that time that said if you made a particular kind of ideal 3-dimensional material, which was an analog to strontium titanate, but where you had, this is technical, a particular atom, a Jahn-Teller atom at the center of the cube, that you might get high temperature superconductivity. So Alex literally said to me in the hallway at IBM, I'm going to discover high temperature superconductivity. This is true. And he said, at some level, that's how I'm going to get back at those people who fired me from my job in the lab. And he told me what the theory was, and I'm not going to repeat it here, but I thought I knew enough solid-state physics to judge for myself that this was a completely wacko theory. And I literally walked away from him, and I'm embarrassed to say this, and I thought to myself, you know, people go into upper management, and they become brain dead. So I cannot explain my subsequent career, and I hope you won't agree with what I thought in 1984. That's literally true. So then 2 years later, he's discovered high-temperature superconductivity. I mean, but he went to do it. So, I mean, how often does that happen in life? But it turned out it was actually a brilliant piece of work because they were trying to make a material called lanthanum copper oxide, but it's LaCuO3, which was a perfect cube. And I know Jun Akimitsu was here. Jun was working in that same territory at that time, right? Of looking at these materials, which were, at that time, people were very interested in them for reasons of catalysis, actually. But he had gotten this idea from a theorist friend that if he took this perfect cube and he replaced the lanthanum by something so he could turn it from an insulator into a metal, but with copper at the center, that it would then become a superconductor. It's a thing called the Jahn-Teller effect for the specialists. Okay. So then Bednorz started making the material, and by phenomenal luck, made a mistake in the chemistry. And they sure enough produced the material, which was predicted to be the high-temperature superconductor, but about 1% of it went into another phase. And that phase turned out to be not what they were trying to make, but something which was almost ideally two-dimensional. And that's the structure of the material of lanthanum 2 copper 04. Now, here's where their genius as experimentalists comes. So I know a lot of experimentalists who had a very well-developed theoretical idea, do an experiment that doesn't fit with the theory, and then they work like mad to adjust their experiment to fit the theory. This is a weakness we experimentalists have. It's our original sin. To Bednorz's credit, and Alex Mueller's credit, they figured out pretty quickly that their original motivation was not correct. And then Bednorz, doing the chemistry, systematically worked to isolate the material that was actually the superconductor, and discovered that it was not what they were trying to make, but something which was a first cousin, but which was perfectly two-dimensional, or almost perfectly two-dimensional. And they understood that the two-dimensionality must matter in some profound way. Then Alex did a second thing, which I think is even, so this he told me personally, even more remarkable. So he knew, because he was a very smart guy, still is, that this was a Nobel Prize discovery. So in our modern era, I give 99 out of 100 odds that there would be a manuscript on the desk of the editor of Nature the next day, right? That's what we do these days, sadly. What Alex Mueller did is he locked the door of the lab and dismissed the technician, because he knew he had made a great discovery, and he wanted the pure pleasure of discovery by himself, the selfish pleasure of discovery, which he knew would only last until someone else found out about his result. And so he and Bednorz spent 9 months without a technician doing the work themselves with the lab doors locked. They didn't tell management, because the worst thing ever would have been to have told management, right? And they just did research on high-temperature superconductivity on their own. And then I asked them, so why did you publish? So then it turned out there's a great chemist at the University of Texas by the name of John Goodenough. People will know him, right? Especially people like Ramesh. And John Goodenough published a paper in the same territory, the same class of materials, and they got scared that they were going to get scooped by Goodenough, who's also a very good scientist, and if he had come across the right compound, he would have got the Nobel Prize. So then they decided to publish, but they were hoping that no American would read their paper, because they knew what would happen. So they therefore published their article, which is a wonderful article if you read it, in Zeitschrift für Physik. Okay. Of course, Paul Chu at University of Houston read the article right away, because he kept track of journals like Zeitschrift für Physik. And then, of course, then we had this explosion. Okay. And specifically, there's Paul Chu's measurements of the resistance in yttrium barium copper oxide, and where you see it's superconducting above liquid nitrogen temperature. And that was a great very important discovery because almost everybody agreed that with superconductivity at such a high temperature, you could never fit that into conventional framework. And then also people became very excited about possible practical applications, okay, of this material because it was above liquid nitrogen temperature and therefore much cheaper to cool. Okay, did I set my watch? Okay, good. So then we saw this explosion. I might point out, by the way, if you look down, you'll see I don't know what would have happened at that time, but there was one great discovery in conventional superconductors, namely magnesium boron 2, which is the highest temperature conventional superconductor, and Jun Akimitsu, sitting here in the audience, is the person who discovered that material, which has had a huge impact in conventional superconductors. So we had this explosion. These are the iron materials, which I'm going to talk about only briefly in a little while. So then there was a huge effort, of course, to understand this physics. First of all, people figured out very quickly that for every single material they found which exhibited high temperature superconductivity, the structure was extraordinarily simple. Namely, there was a layer of copper oxide, and I'm going to show you a picture of that in a minute, and then some stuff in between. And the stuff played the role of donating the carriers that made the insulating copper oxide into a superconductor. And so people almost exhausted the list of possible materials within 1 year because they went to chemistry books and materials books, started synthesizing everything, but they all had this common structure. And in fact, the single layer of copper oxide looks like this. And it's very, very simple. So you have copper atoms, and there's only one hole, and that hole sits in an orbital that looks like that, the x squared minus y squared. So that could not be simpler. And then there's the oxygen. And the oxygen has the two orbitals, the green and the blue. It turns out that the active one is the blue. But the problem, from the point of view of conventional theories of superconductivity, is that every single copper has a spin. It's a single hole, so it has a spin. But I showed you data from Brian Maple that showed if you had just 1/2 of 1% of impurities, that destroyed superconductivity. And then suddenly we find a new family of superconductors where every single copper has a spin. Now, the first thing that happened is that everybody tried to imagine away the spins and fit these materials into the conventional picture. Because most physicists don't like things that are genuinely new and original. And so they worked desperately to fit them into the traditional framework. And so at that stage, Mark Kastner, Mark, where are you? And Mark was down the hallway from me. We're watching this. I won't give all the reasons why some work Mark and I had done together meant we knew that the entire community was going down the wrong track. We just didn't know what the right track was at that time. Right? And then, I can't remember if we did it independently, Mark, or who pointed out, you probably pointed out to me, you were usually better. Then we read an incredible article by Phil Anderson at Princeton, who said, this is a new form of matter, it's a new form of superconductivity, and it rests on what he called a quantum spin fluid. So in his picture, the fact that the system has spins is at the guts of whatever theory is going to work for the superconductivity. So this got Mark and me very excited, and then we decided we would start doing some systematic studies of the high temperature superconductors. And I'm not going to have time to dwell on it at all. There is one thing I'm very proud of, which involves 3 of the speakers tomorrow: Sudeep Chakrabarty, CHNS Sudeep Chakrabarty, Bert Halpern, and David Nelson. So at that time, we actually didn't have a theory for quantum magnets in 2 dimensions. There was no theory. Phil Anderson had this heuristic idea of a quantum spin fluid. No one knew if it was right or wrong. So Mark and I and Gen Shirani and some others decided that we would study the magnetism in the pure system first without looking at the superconductor. And we got very extraordinary results in which you could see the material was almost perfectly 2-dimensional, and you could see the way in which magnetic order developed in these 2-dimensional sheets. And I gave a solid-state physics seminar at Harvard about this. And Sudeep got very excited about it, and then ran off. And he and Bert and David did a wonderful theory using field theoretic techniques, quantum nonlinear sigma model, and he essentially solved the problem exactly. The prediction, unfortunately, was that Phil Anderson was not correct, and that actually the spins, even though they were quantum, ultimately would behave classically in a very, very beautiful and elegant way. And so they solved this exactly, and we measured the way in which the magnetism grows. It's too technical to explain why that graph shows it, but basically their theory is the solid line without any adjustable parameter. And it was the single best theory we ever had in magnetism, actually, for phase transitions in magnets. But it did, I don't know, Sudeep, maybe this sounds too negative, but their theory in a way proved that it wasn't interesting. It was elegant and beautiful, but not profound. Sudeep, or Bert, is that too harsh?
Go ahead, I'm not going to say.
Okay. It was a very, very beautiful theory, which has inspired led to quantum critical points, and has led to all kinds of stuff since. Okay. So anyway, so we did this. Then we started doping. And as soon as you add charge carriers, you get an extraordinarily complicated phase diagram. So what you find is you start out with this two-dimensional magnet. You add 2% carriers, and the magnetic order goes away. And then you get up to about 5.5%, and it becomes a superconductor. And then you keep going, and then ultimately the superconductivity goes away. And you find in the middle of the superconducting area, you get very unusual properties, which were first recognized by Chandra Varma, who's here. Chandra, saw you back here. Chandra, there. No, the other. There's the husband. They separated for some reason. I don't know what this means. And so all kinds of new ideas got introduced to physics. So then the challenge became, how do you explain this phase diagram? And we did a pile of measurements, and I'm already running late on time. So I'm not going to go through the details, but let me just jump to that picture. So one of the beautiful pictures that emerged was that the carriers in the superconductor isolate themselves into linear chains. That's called the stripe model. And that picture, Steve, that's your picture, I think, actually. And came from Vic Emery and Steve Kibbleston. And the measurements I just skipped over show the evolution of the chain structure as a function of the number of electrons you have. And they agree quantitatively with what Steve and Vic had predicted in advance. So, and again, Steve, you're going to have to forgive me. But so I thought, well, we've almost solved the problem, right? Because they made these predictions, et cetera, right? But if I asked Chandra Varma, is this a solution? He would have said, are you nuts? And Chandra will give you a separate theory. Doug Scalapino will give possibly another. And Morris Rice couldn't make it here. And I recently listened to Morris Rice, who's a great European theorist, tell me how they were all wrong. Okay. So, and maybe one of them can stand up afterwards and tell us what the correct description is. But basically, the bottom line is after 30 years of extraordinarily hard work trying to understand one single sheet of copper and oxygen, right? We've been unable to come to a satisfactory description of what the origin is of superconductivity in these very novel systems. So now I'm going to fast forward to my time here at Berkeley. Even though, so this went on for 20 years of lots of hyper smart people trying to figure out the physics of a single sheet of copper and oxygen, doped, right? Without, maybe one of the theories that exists is correct, but there's no agreement among the community yet. But I at least was convinced that high temperature superconductivity and this exotic phase diagram was unique to this single sheet of copper oxide, and that there were special characteristics of this two-dimensional magnet that gave rise to high temperature superconductivity. And when I started my research program here at Berkeley, then I had various ideas of exploring that further, and so we were then focusing on understanding copper oxide superconductors. Then an extraordinary thing happened, and that's these red dots. So in 2008, so this is very recent, some people in Japan discovered some new high-temperature superconductors based on iron. First at 26 Kelvin, then all the way up to 56, and then most recently, some claims in a single layer of iron selenide as high as 100 degrees Kelvin. And if you look at the materials, on the left-hand side is what we now think of as traditional copper oxide superconductors, and on the right-hand side is an iron arsenide superconductor. And you see there are some analogies. But I'm not going to go through all the technical details, but that's where the analogy ends, actually. Okay. There are many of these materials. So this is an experimentalist's dream, because there are so many different materials in this general category. I'm not going to say it's easy to make single crystals, but in Edith's lab, right, Edith Burry sitting here, my students and postdocs have managed to grow cubic centimeters of these high-temperature superconductors in very high-quality crystals. Okay. Let's see. And if you look at the phase diagram of one of them on the right, it's eerily similar to the phase diagrams of the copper oxides, in spite of the fact that the underlying physics is completely different, except for one commonality, which is that you start out with an antiferromagnetic material. Although in this case, you start out with a metal, not with an insulator. And again, the magnetism and the superconductivity are mutually exclusive. Okay. This is just resistance measurements that from, I guess, James, it's your data, actually, James Annelides' data, which show that the materials are metals. This is James Annelides' phase diagram. And so you get a generic phase diagram which is closely similar to that of the copper oxides, but with everything else different. Okay? So that must mean, to me at least, that this fine details of the crystal chemistry of copper oxides to make high-temperature superconductivity must be wrong. I mean, it makes high-temperature superconductors, but obviously we need a much more universal explanation. Okay. So, and there are now very fancy theories for it. It turns out that the physics of these materials is more complicated because there are multiple order parameters. And there's things analogous to pneumatic phases in liquid crystals, et cetera. So we're now building up a sort of library of information about this new family of high-temperature superconductors, which were discovered completely serendipitously, right? And no one had even the remotest idea that this might happen. But the generic geometry of the phase diagram is closely similar, which again tells you that the fine details can't matter. Our work in this got started by two people in this room right now, Stephen Wilson, Castell Rotundu. Where are you? Somewhere. There's Castell up there. I had a really interesting thing happen, which pushed us all the way. So my entire research program now is trying to figure out the basic physics of these materials. And that happened with a third person by the name of Jun Zhao, very talented postdoc. So we were splitting our time between the copper oxides and and these iron materials. And Jun was supposed to be doing a particular experiment on the copper oxides. And he came to me and he said, the copper oxides were your generation's problem. And you didn't solve it. And he said, basically, I'm 28 years old, Chinese, my countrymen just discovered these. I want to work on these. I don't want to work on your problem. So this literally happened, which is not how you might view some of you Chinese culture traditionally, right? So I sat there in my office. I was still chancellor, so this happened in my chancellor's office. And I said, any postdoc with that much chutzpah, right? He reminded me of when I was 28 years old. So I said, fine, good. We're completely quitting working on copper oxides. We're only going to work on this new class of materials, and that's what we do. And Jun is now a young professor at Fudan University, doing very, very well. So I'm going to skip through. This turns out to be extraordinarily rich, this class of materials. It is literally an experimentalist's dream. I mean, it's wonderful for young experimentalists because there are so many new systems, and we don't understand what the thread is that ties together the iron-based materials, much less their connection with the copper oxide superconductors. So, but what we do know is that in the iron materials, they're all antiferromagnetic, but they can be semi-metals or narrow bandgap semiconductors. In these materials, I didn't show this to you, but the magnetic and structural transitions are intimately connected. That's not true in the copper oxides. I didn't document it for you or show you the data. It's one of the slides I skipped over. But the one thing that's in common is the magnetism is the same in all of the parent materials. In all of these materials, antiferromagnetism and superconductivity compete. The phase diagrams have a remarkable similarity to those of the copper oxides, but it's not identical. So that asks an important question: is there a universal model? So just like my 28-year-old postdocs wanted to be liberated to do what they wanted to do and solve their generation's problem, let me just say to all of the, you don't have to be under 30, but approaching that, this is a great problem in physics, quantum many-body physics. And to a certain extent, it's true that our generation has not succeeded. So this is a phenomenal opportunity for young physicists to do something that's profound and is completely new and completely unexpected. So let me say, finally, one of our lessons is, and this is in part from my material science colleagues, that if you look at the history of solid-state condensed matter physics over the last several decades, right, including especially the field of superconductivity, most of the interesting problems have originated either from the discovery of new materials or from the discovery of new properties of old materials, like Jun Akimitsu's work on magnesium boron 2, or beryllium boron 2. Secondly, and this is a sales pitch for neutron facilities, which I'm about to make at DOE in a week, is that every time we discover new material, one of the probes we always need is neutrons from a nuclear reactor, because we need to know what the structure is and we need to know what the magnetic excitations are. So with that, I thank you for being such an attentive audience.
Okay, now's the time for me to get some exercise. We have plenty of time for questions, so if you have a question, please raise your hand. I will come around with the microphone, so please wait for me to come to you to ask your question. So, anybody want to start? I will start. So were the irons, so the iron sounds really interesting. So has it, to you, is there some fundamental connection between the iron materials and the copper materials that you're trying to pursue to sort of band the gap between those?
Yes, but if I could state it coherently, I probably would have solved the problem. My instinct is that we, and this really came from a theorist at Harvard, that Subir Sachdeb, that it may be that we're not thinking about these materials right, any of these, this whole phenomenon of high temperature superconductivity properly, and that we're trying too hard to put it into a BCS-like mode. And it may be that this is a quantum many-body system, and this is one of the ground states, and that we shouldn't just try and think perturbatively, and that the iron materials are sort of one class where one of the ground states is the superconducting state, and the copper oxides are another, and probably someone else will discover another. But to translate that from just words into some kind of theory, of course, it's not trivial. I mean, people talk about replacing the phonons by magnetic fluctuations, but that hasn't led anywhere. And so we put that in our first paragraphs of our papers, but I instinctively don't believe it.
Are the iron compounds got striped phases as well?
So one of the experiments Zhizhen Zhu is in the audience here that he did is he showed in the iron selenium tellurium system you get beautiful stripes, and if you have the stripes there's no superconductivity, and if the stripes collapse and become commensurate then it becomes superconductor, the exact opposite of the copper oxides. So we see stripe-like phases, we see incommensurate phases, but they don't correlate with superconductivity the way the other materials do. And we're arguing about this in real time right now, whether or not, again, that's profound or just some peculiarity of the Fermi surface. So we don't know that yet. So people see commensurate signals, they see incommensurate signals, but there isn't the kind of phenomenology which is now very rich, which exists in the copper oxides.
If I can overstate your remark about cuprate high temperature superconductors, that the high temperature is not the most important part. Are we dabbling with the idea that maybe superconductivity is not the most important manifestation of the physics that's going on here, but something collateral, and these are different, that superconductivity isn't the right thing to be looking for as an explanation?
Well, I guess I might have rephrased it. That was partly what I was trying to get at with Sachdev's idea, which is that these are quantum many-body systems. They have different ground states. And the system has to make a choice between what ground state it's going to go into, and superconductivity happens to be one of them. You know, you might have said, actually, you know, you love magnetism, so you think the magnetic state is much more interesting, right? So that's a sort of way of saying it, I guess, right?
But is there such a thing as a superconducting ground state? Are there different types of things that could exhibit that?
These exhibit all the conventional properties of type 2 superconductors. And so, you know, you have effective charge of 2e, and you have vortex lattices, et cetera. So from the broken symmetry point of view, right, these have the broken symmetry properties of conventional superconductors, right? The phase diagrams are very unconventional, but if you put it in a black box and measured it, and someone told you that this was niobium 310, you would believe it was niobium 310 in every measurement that you did. And that's I'm glad you asked, because that's actually a very important statement, which I didn't make because it's more for the specialists, that from the broken symmetry point of view, these, well, you get wave instead of S wave or S plus minus, but that's a fine detail.
I'm not going back to put some pressure on our students, but I was going to ask, you never mentioned what got you inspired in condensed matter physics in the first place. So could you give us a little of your background?
That was my summer job when I was 21 years old. And so I was, you know, a summer student at Chalk River, and Bert Brockhaus and Mike Rowe was there. And Bert Brockhaus had just invented the triple axis spectrometer, for which he got the Nobel Prize. I mean, he did some basic measurements with it, but me and another kid were the first ones there, sort of, right? And I got to do some measurements then. And first of all, I thought it was amazing. By the way, for students here, I didn't know what lattice dynamics was when I went to do this experiment, and so I spent my first month with Cattell's. I think it was, I don't know if it was 1 or 2, so other student and I taught ourselves the theory of lattice dynamics out of Cattell's book. That was my first contact with Berkeley. And so I learned lattice dynamics. I was a pretty good programmer, so I knew how to write programs. And actually what I learned from that experiment is, you know, I'm not one of these people who ever was interested in rebuilding an engine or ever could build an engine from scratch. But I learned that there was a role for people who were not very good at experiment and not very good at theory, but could somehow put them together if they had good intuition. And condensed matter physics was a field which allowed that. And you could do it with a buddy, right? And so, you know, the social aspects of physics as well as the intellectual aspects is something that I would say I've enjoyed throughout my entire career. And I've liked doing research where you have 2 or 3 pretty talented people, hopefully more talented than you are. And so condensed matter physics allowed that. And then the field has turned out to be very rich, and a lot of, exciting things have happened during my career in fields of liquid crystals, surfaces, et cetera. Right? So, right.
More questions? Yes.
Did you mention why they looked at iron instead of something closer to copper, like cobalt or nickel? Like, was there a particular reason why they focused on
It was an accident.
an accident?
They were the original measurement where they discovered the superconductivity. They were looking at, I think, thermoelectric properties. They were looking at something else completely different. They just happened to measure the resistance down to low temperature, and then discovered it was a superconductor. They weren't people who worked in the field at all. And then there was this monsoon in China, in Shanghai and Beijing. I mean, it was a veritable monsoon where Chinese universities are now in an extraordinary situation. They have great equipment, they have hyper smart young people, and then they just started making materials like mad, and then they discovered almost all the materials that I showed you were discovered in either Shanghai or Beijing, actually. So it's been an interesting piece of sociology, I have to say, which has been fun. Ben.
Relating to that discovery-based science that you brought up earlier, is in terms of funding in this country, could one have been sort of funded for this type of research that the Chinese did in discovering these materials in this country, or would it be much more difficult?
It's a lot harder. So if you ask, yeah. So the question is, it's this issue of, which Jim Simons and I have been discussing extensively. So, Jim Antiferromagnet and I were discussing actually the beginnings of my liquid, when we worked in liquid crystals, where, let me give the aside first. So Dave Litzter and I and some others did research which became very famous in the field of liquid crystals. When we wrote the original proposals, we got told by a famous University of California professor that there would never, ever be any physics in liquid crystals. So you should not fund this research. And the NSF funded it nevertheless, right? That cannot happen now. And so truly, it's very difficult to get really creative, speculative research funded because a referee can always disagree, right? And so if someone had, if you got a proposal and someone, Alex Mueller never could have got his research funded in the United States. He just never could. Because it was, as I said, I talked to him in the hallway. As far as I was concerned, if he had sent me a proposal to referee, I'd say this was a crackpot idea, because I could see immediately why the theory that motivated his experiments was not correct, and it wasn't correct, right? But he made a serendipitous discovery because he's a really good physicist and was going in the right direction. And so we have a fundamental problem with the peer review system and with funding of research in the United States right now, which is there's too much pressure for it to be quote unquote relevant. And secondly, the peer review system militates strongly against people who want to do really speculative things where it's your intuition and you can't, you can't write down a coherent argument that, will convince people you're right. Because if it's really creative research, there has to be reasonable odds that you're going to be wrong, right? And so people have to be willing to fund, agencies have to be willing to fund research that has a fair probability of being incorrect, right? So what Jim and Marilyn and I and others have been looking for is new sources of funding, primarily philanthropic, that will be focused on truly speculative research. And we'll have that as a criterion. We call it discovery-based research. And I was chiding Nick about this. We've banished the word innovation. If you say it's innovative, we won't fund it. It has to be attempting to do discovery. So it is a profound issue, I think right now, at this stage in history. As far as I can tell in China, several of my young people from my group have gone back to China. They're doing whatever they want, and they're very well funded. And they don't seem to have to justify it. So.
Do you think those discoveries in China could have any effect on funding in the US, ultimately?
We'll see. We'll see. We'll see.
Yes.
40 years ago, one could state that superconductivity was the most well understood problem in solid state physics. And I'm sure you're hopeful, but are you optimistic that in your lifetime that statement will become true again?
So that's a really difficult question because I first have to figure out what my lifetime is. And I'm not optimistic, actually. I'm not optimistic. I mean, given how hard the copper oxides have proven to be, and these new materials are so much more diverse in their properties, and so I think it's going to take a while. I mean, it's great for young people. I'm sure there are parallel things in other fields, right? This is the one field I know well, but I think this is fabulous for young people because there are so many new systems, and you know analogs in 2 dimensions and all of that, right? You and Fang, et cetera. So it's a sort of a resurgence. You know, my mentor in physics, besides my thesis advisor, was a great physicist by the name of Gen Shirani, who unfortunately passed away about 5 years ago. And he said in his career, which spanned almost 60 years, that every 10 years, something completely unexpected would be discovered. And then he would get revitalized. So he'd get bored, and then sort of on an almost regular cycle of every 10 years. And we're seeing that continue to happen, which I think makes me very hopeful for the future. I'm less hopeful about people in Washington. So that's for many reasons. Is this being televised? Filmed? I was going to make a comment about Sacramento, but I'm going to leave it just in case I get Nick into trouble. So, okay.
We got the mic right here. So,
yeah.
Okay, one last question. Anyone? Yes.
Besides board games, what are the applications of superconductors?
Well, they're limited by your imagination. Obviously, for lossless transmission of electricity, for storage for power storage. There's a whole long list of things which people tried to produce in companies like American Superconductor, et cetera. But it turns out that the yttrium, barium, copper oxide family of superconductors and materials are brittle, and it's a material science problem. I'm actually hopeful that these iron-based materials will be much friendlier from the point of view of applications. And there will be a whole wide variety of them. But manifestly, if someone finds a material that's superconducting above room temperature, then it's games is one thing, but it's almost limitless, the possibilities of things that you can think you can do, either using the perfect conductivity or the Meissner effect. Maybe more with the Meissner effect. I mean, trains, for example, right? So in Japan they have maglev trains. But imagine if you didn't need coolant to cool the track, to cool the magnet, and if you could have it above room temperature, so you could have trains that could go at 400 miles an hour without resistance, et cetera. Good. Even Jerry Brown could get his legislation passed.
Well, on that optimistic note, thanks again, everybody, for joining us, and let's thank Bob Birgeneau once again. So.